in any group, by far the most important subgroups are the normal subgroups. So this is the topic for today. So let G be a group and H be a subgroup of G. Then we say that H is a normal subgroup of G if for every little g in G, the left coset of G in H is equal to the right coset. We've seen that this is not always the case. So these groups which satisfy such a property for every little g in G are sort of special. And in fact, not only they're special, but they are very important, as we will see in the next lecture when we talk about quotient groups. We'll have a special notation for normal subgroups, namely we augment this sign by this little vertical stroke here to denote normal subgroup. So what are the examples of normal subgroups? So there are some that are sort of obvious. So let's just write them. Let me just write them in the series of propositions. So G will be a group always in these propositions. G is a normal subgroup of itself, and the trivial group is also a normal subgroup of G. Well, why is that true? In the first case, right, there's only one coset, namely G. So any little g I take, little g times G is equal to G. So there's just one left coset and one right coset. What about the second thing? So proof, if so H is equal to G, then there is only one left and one right coset. Of H and G. On the other hand, if H is equal to just the identity and G is in G, then let's see, G times the coset times the subgroup consisting of just the identity that's just a singleton, G. That's the coset. So that I can rewrite as EGG, which is then EG G. So we see that the left cosets are equal to right cosets. Okay, so that's a very, very simple example of a normal subgroup. The whole group and the identity and the trivial group are normal subgroups. Proposition 2, any if G is abelian, then any subgroup of H is normal. Any subgroup of G is normal. Okay, so here the proof is also very easy. So let H be a subgroup of G, and let G be in G. Then GH consists of the elements GH where H is in G, when H is in H, by definition of what that left coset means, but that is the same because I can commute the G and the H, so that's the same as HG when H is in H. So that is by definition the right coset. Okay, so in an abelian group, every subgroup is normal. But beyond that, there really aren't very many easy examples of normal subgroups. That is, one has to work to be able to come up with examples of normal subgroups. And the reason for this is somehow because the prize is also quite big. You will see in the next lecture that having a normal subgroup, it's sort of like having a little gem there that will allow you to do something really interesting about the group. in some sense, learn something more about the structure of the group. We'll even see this in just a moment, in a little bit, that normal subgroups are actually quite important. So beyond these two propositions, there aren't any obvious ones, any obvious examples, but there's still some things that one can do. So recall, so let's write proposition 3. Any subgroup of G of index 2 is normal. What does that mean? So by definition, the index of H and G is the number of cosets, of left cosets of H and G. But as we shown in the last lecture, the number of left cosets is the same as the number of right cosets. So that means that the subgroup only has 2 left cosets and 2 right cosets. So let's prove this proposition. So let H be a subgroup of G of index 2. Then there are only 2 left cosets and only 2 right cosets. Of H and G. Okay, but I can actually list them what they are. So left cosets. One left coset is always the subgroup. So H. Okay. Because left cosets are always equal or disjoint, the other coset has to be disjoint from H. So what is in this other coset? There are only 2 cosets of H and G, so that means in the other coset you must have all the elements of G which aren't in H. So I'm just going to write it like this, G minus H. By this I mean all the elements of G which aren't in H. Right? Again, the cosets are always disjoint. I mean, distinct cosets are disjoint. And the union gives you the entire group. So that means every element of G must be in one of the cosets. So it's either in H, which is one of the cosets, or in the other, or it's in the other coset. So that is the other left coset. What about right cosets? Again, one right coset is always the same, H. And because there's only one more left, it must be the same as this one. So the left cosets and the right cosets are these 2. So now let's prove that the group is normal. So let G be in G. So if G is in H, then we know that the coset GH is equal to H. And that's also equal to the coset HG. Otherwise, if G is not in H, then GH cannot be equal to H, because we know that GH is equal to H if and only if G belongs to H. So that means GH must be the other coset. But that also must be the coset HG, because again, HG, the only other option for HG would be to be H, but HG is equal to H if and only if G belongs to H. And that is not the case. So these 2 cosets are also equal. So we're done with this statement. So that means, so for example, we discussed last time the subgroup A3 consisting of the identity and the 3 cycles inside the group S3, and now I see that the subgroup must be normal because the index of A3 in S3 is 2. In fact, in the examples last time we actually proved directly that the subgroup is normal. That means the left cosets are equal to right cosets. But because of this proposition, now we would know it without ever checking it. So the next proposition gives a very important example of normal subgroups. So proposition 4. So let G and G prime be groups let phi from G to G prime be a group homomorphism. Then the kernel of phi is a normal subgroup of G. So kernels of homomorphisms are normal subgroups. And this is part of what I was going to elaborate on in a future lecture about the importance of normal subgroups. So in particular, if I have a homomorphism, then its kernel is a normal subgroup. So maybe that gives me a big supply of normal subgroups. Well, maybe, except homomorphisms are also not so easy to construct. In particular, if I can construct a homomorphism from one group to another, that means that I have found some relation between these two groups. I was able to somehow map the first group into the other group. So homomorphisms are not, except of course when this group is cyclic, for example, then we have actually proved how to construct all the homomorphisms. But in general, homomorphisms are not that easy to construct either. And we're going to prove later, not in this lecture, but in a later lecture, that in fact there is, not only are kernels of homomorphisms normal subgroups, but every normal subgroup is a kernel of some homomorphism, is the kernel of some homomorphism. So it's in a sense equivalent constructing normal subgroups and constructing homomorphisms. All right, let's prove this proposition. So proof. So write H for the kernel of phi, and I already know this is a subgroup of G. This is something we discussed before. So now I just want to show that it's a normal subgroup. So how do I show it? So I take any G in G, and we want to show that the left coset GH is equal to the right coset HG. So here's what I'm going to do. I'm going to look at phi of G, H, G inverse for some H in H. So let H be in H, an arbitrary element of H, and I look at what happens, what the homomorphism does to this element. Because it's a homomorphism, I write it this way. And now remember that the powers on homomorphisms come out. And secondly, what is phi of h? Well, h, little h is in h, and the big H is the kernel of phi. So this is the identity in G prime, as H belongs to kernel of phi. So that means these two guys together, these three guys reduced to these two. So it's phi of G inverse. So that's the identity in G prime. So what does this show? So GHG inverse belongs also to the kernel of phi, so to H. i.e. GHG inverse is equal to some H prime that belongs to the group H. So GH is equal to H prime G. Which means it belongs to this coset. H prime comes from H, and there's G. But because little h was arbitrary, as h was arbitrary, we get that GH, therefore, is a subset of HG. Okay, so what we have achieved is one containment. GH is contained inside HG. How do I get the other containment? Well, I look at a similar expression, except I put G inverse first. And you see this is also equal to EG prime. Same calculation. Just do the same calculation on this and you will also get EG prime. So G inverse HG belongs to H, i.e. G inverse HG is equal to H prime for some H prime in H. Hence, HG is equal to GH prime, multiplying on the left by G. And this belongs to GH. And again, as H was arbitrary, we get HG contained in GH. Okay, did we get what we needed? I think so. Here's one containment. Here's the other containment. So from these we get, so GH is equal to HG as claimed. Okay, and this finishes the proof of the proposition. So kernels of homomorphisms are normal subgroups. At this point, I cannot yet show you that every normal subgroup is the kernel of a homomorphism. For that, we need to develop a little bit more of theory. Okay, so we have a few possibilities where we have normal subgroups. First of all, the whole group and the trivial group are always normal. Inside an abelian group, every subgroup is normal. Index 2 subgroups are normal, and kernels of homomorphisms are normal. What else? So let's do proposition 5. Actually, let's make a definition first. So let G be a group. Set Z of G to be all the elements in G which commute with everything. These are the elements which commute with everything. Z of G is called the center. Of G. Okay, and I'm leaving it here as an easy exercise for you to show about the center. So exercise. One, show that C of G is a normal subgroup of G. And exercise 2, show that any subgroup of Z of G is normal in G. So for the first exercise, you have to show two things. First of all, that Z of G, the center, is a subgroup, and secondly, that it's normal. So its left cosets are equal to right cosets. And for the second thing, you show that any subgroup of the center is normal. I just wanted to give, so we're going to give some examples of this, but one obvious example, note, G is equal to its center if and only if G is abelian. Okay, that's clear, because if G is abelian, then every element commutes with every element. So that means G is equal to the center. On the other hand, if G is equal to the center, by definition, that means every element of G commutes with every element, so G is abelian. Okay, so that's clear. But for other groups that are non-abelian, they may have a center, so elements that commute with everything. I wanted to give one more example, or actually two more examples of normal subgroups, but they're all related to the same group. So I'm going to make a definition here. So definition. So we denote, so set GLN of the real numbers to be the group of, the group of n by n matrices with determinant not equal to 0 under multiplication. First of all, you know that you can multiply n by n matrices. This is actually completely inessential that I put real numbers there. I could have put any field, or for that matter, yeah, I mean, with this definition, I could have put any field. But because we never talked about determinant or matrices with entries in other fields, then, I mean, with entries in any field, and you know from linear algebra, matrices with entries in the real numbers and how to compute what determinant is and how to compute it for these. So I'm just going to stick to this particular case. So you know that you can multiply n by n matrices. So multiplication gives you a binary operation on the set of n by n matrices with entries in the real numbers. This multiplication is associative. That's something you checked in the linear algebra course. The identity matrix is the identity element. So how do you know that every matrix has an inverse? That's guaranteed by the fact that the determinant is non-zero. So these are the invertible matrices. I should also mention, right, that in fact, if you take two n by n matrices with non-zero determinants, you get a matrix with non-zero determinant. So this really is the multiplication of n by n matrices really is a binary operation on the set, on the subset of n by n matrices with determinant non-zero. Okay, so this is a group under multiplication. I'll leave the details to check for you, but I more or less explained why this is a group. So I can look at the following subgroup. So let H inside inside GL and R be the subgroup consisting of scalar matrices. What is a scalar matrix? Well, that's a matrix that looks like, so i.e. matrices of the form A, 0, 0 for some A, for some non-zero A. So if I write in units in R, then that means non-zero, right? Because the units inside the real numbers are the non-zero real numbers. So the same number along the diagonal and 0 everywhere else. This is clearly a subgroup because if I take two matrices of that form, I get a matrix that also looks like that. And the inverse, of course, the identity matrix is like this, and the inverse to every such element is an element which has the inverses of A down the diagonal. So I claim, so note, H is actually contained inside the center. So that means scalar matrices commute with any matrix. All right, I'll leave that for you to check as well. You know how to multiply matrices, so you can just as well check that that matrices, the scalar matrices, commute with every matrix. So they are a subgroup of the center. So hence, the scalar matrices actually are a normal subgroup. Of GL and R. One can in fact prove that the scalar matrices are the center, but we're not going to get there. Let's take a little break and then we'll have one more example.